Okay. Now, yep, everything is live. Good. Yeah, welcome back. So this is day 3 of Advent of Code. Um, I haven't been reading the Advent of Code NIM room, but I popped in there earlier, and it seems like this one is harder than the two first ones. People are surprised by how much of a step up in difficulty it is. So this will certainly be interesting. Again, same as always, I haven't looked at this before. I'm not cheating. I haven't looked at the task. I have nothing prepared. So let's dive into it. Oh yeah, and I updated the GitHub repo with my day 2 solution. So if you want, you can now check out yesterday's solution in the repository. Right. So let's dive in. Binary diagnostic. The submarine has been making some odd creaking noises. Ooh, that's not great. So you ask it to produce a diagnostic report just in case. The diagnostic report, my puzzle input, consists of a list of binary numbers which, when decoded properly, can tell you many useful things about the conditions of the submarine. The first parameter to check is the power consumption. Okay, so we apparently need to do some binary logic, maybe? You need to use the binary numbers in the diagnostic report to generate 2 new binary numbers, called the gamma rate and the epsilon rate. The power consumption can then be found by multiplying the gamma rate by the epsilon rate. Okay? Each bit in the gamma rate can be determined by finding the most common bit in the corresponding position of all numbers in the diagnostic report. For example, given the following diagnostic report, consider only the first bit of each number. There are 5 0 bits and 7 1 bits. Since the most common bit is 1, the first bit of the gamma rate is 1. Right. So that is just whichever is most common. The most common second bit of the numbers in the diagnostic report is 0. So the second bit of the gamma rate is 0. So on and so forth. Yeah. So that's the gamma rate. The epsilon rate is calculated in a similar way. Rather than use the most common bit, the least common bit from each position is used. So if epsilon rate is 0.1001 or 9 in decimal, multiplying the gamma rate 22 by the epsilon rate produces power consumption 198. Use the binary numbers in your diagnostic report to calculate the gamma rate and epsilon rate. Then multiply them together. What is the power consumption of the submarine? Right. So, I mean, immediately, the epsilon rate is obviously just the inverse of the gamma rate, because the least common bit is going to be, like, since this is binary logic, the most common is going to be the opposite of the least common. So this is just a not operation on this number, which is interesting. So we just need to calculate the most common ones. Is there a smart way of doing that? I wonder. Yeah, let's just do it in the easy way. So let's grab our input. Again, the inputs are different for each person, so these will be different for you. And here we have 4 8. Okay, so we have 12 bits. It's an odd number. Right. So now we have the input here. We can go with part 1. We are probably going to be using string utils again. So let us create a count array of 12 bits. That will just count how many of them there are. And then let's just also create a line counter to start that out at 0. So again, in nim, everything is binary 0 initialized. So defining an array of 12 integers, these will all be binary 0. So the entire array will be like it will be 12 zeros in this array. Now we can do for line and input.txt.lines. And now we can do for C in line, so for the character and the line. I'm going to do IC. So when you do this will be the character in line, because line here is a string. If I do this, so doing this is the same as calling the items iterator on the line string. Doing this is the same as calling the pairs iterator on the string. And what the pairs iterator does is that it returns a tuple of an index and the character. So now we can do count I plus equals if C equals 1, 1, else 0. So now we're basically counting all the ones in our sequence. I think these will have the new line character split or not present. I'm not 100% sure. If not, this will crash because we only have 12 positions. So 0 through 11. And then after, and we also want to count our lines. Okay, increase the line count there. Then we can down here for I in count. Actually just do this. Count and then set count I to be value divided by line count. So division, this is division without remainder. And I believe let's just check that real quick. So I believe this should do if I have 12, for example, and divide that by 4. Yeah. Wait. What is this number? It is divisible by 4, of course. Divide by 5. 2.4. Okay, so this should give me 3. Oh, it rounds up. Do we want that? If it rounds everything up, this will just always be 1. Which is not what we want. Okay, so let's just do if value is greater than line counts divided by 2, then 1, else 0. So basically what we're doing here is if the value is larger than half of the amount of lines that we have. So if more than half of the lines is a 1, then we set this to a 1, otherwise we set it to a 0. And actually, let me do gamma rate 0, and we don't do I, but gamma rate is equal to gamma rate shift left 1, or this number there. So basically what we're doing here, first gamma rate is 0, then we shift all the bits 1 position to the left, still 0. Then we do a binary OR. So if the bit is 1 in either of the two numbers, it's set to a 1. So we shift it left 1 position. If the value of this one is blah blah, we do a 1. So that would be a 1 in the 0 position of the bit. And add that as the last one, and then shift the whole thing again. So that should be our gamma rate sorted out. Oop. What? Why doesn't it like this? Do I have to wrap it? Yeah. Okay. And then, of course, our epsilon rate is, but we can't not this. Like if I did not gamma rate, that would also do all the bits before the 12 last bits. So remember, we only have 12 bits. What we can do is so this. So 4, 8, 12 bits are set to 1. All the others are set to 0. And then we invert the gamma rate, and then we mask off only the bottommost 12 bits. So that should give us our epsilon rate, and our final score is of course these two timed together. We actually didn't end up using that. I was thinking we could like parse the numbers in as binary or something. Oops. So this should theoretically be our answer. If it's not, we can try with this input and see if that changes anything. Hey! Well, that was easy. Yeah, so this kind of stuff might look a bit confusing, but if you're used to binary logic, it's not that bad. Of course, these are strings, which are kind of weird. Like we could have read them in as binary numbers, like parse them into a number structure, and then having sort of done like do this on the binary numbers instead. But that would be a bit like it would be more finicky than this, essentially. Right. Okay. So let's copy part 1 over to part 2. And then we want to open part 2. Now we can edit this and not destroy our part 1. So part 2. Next, you should verify the life support rating, which can be determined by multiplying the oxygen generator rating by the CO2 scrubber rating. So now we have two more numbers that we have to compute, probably. Both the oxygen generator rating and the CO2 scrubber rating are values that can be found in your diagnostic report, obviously. Finding them is the tricky part. Both values are located using a similar process that involves filtering out values until only one remains. Before searching for either rating value, start with a full list of binary numbers from your diagnostic report and consider just the first bit of those numbers. Then, keep only numbers selected by the bit criteria for the type of rating value for which you are searching. Discard numbers which do not match the bit criteria. If you only have one number left, stop. This is the rating value for which you are searching. Otherwise, repeat the process considering the next bit to the right. The bit criteria depends on which type of rating value you want to find. To find oxygen generator rating, determine the most common value, 0 or 1. The most common one in the current bit position, and keep only numbers with that bit in that position. If 0 and 1 are equally common, keep values with a 1 in the position being considered. If they're equally common, keep values with a 1 in the position being considered. So this is basically what we do here, since we use div instead of rounding, I believe. So if we divide this, the amount of lines. Wait, how many lines do we have? Do we have an odd or even number? Okay, we have exactly 1,000 lines. So we have an even number of lines. So this would be 500. So if our value has to be greater than 500. So what we want to do here is actually greater or equal to 500. Which, that didn't change the number for that task. Not that it was a requirement for that task, but so this means that if they're equally common, so if it's exactly 500, then we keep the values with a 1. Of course, when we start filtering out, this won't stay as 500. To find CO2 scrubber rating, determine the least common value, least common value, 0 or 1 in the current bit position, and keep only numbers with that bit in that position. For example, to determine the oxygen generator rating value using the same example diagnostic report from above, start with all 12 numbers and consider only the first bit of each number. There are more 1 bits than 5 bits, so keep only the 7 numbers with a 1 in the first position. Then consider the second bit of the 7 remaining numbers. There are more 0 bits than 1 bits, so keep only the 4 numbers with a 0 in the second position. Blah, 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 until we have only in the 5th position there are an equal number of 0 bits and 1 bits, 1 each. So find the oxygen generator rating, keeping the number with a 1. So that's this number. Now there's only 1 number left. Stop. Technically you don't have to stop at this point, because looping this, like running this to the end for just 1 number, it will always be the most like whatever is here will always be the most common one because it will occur in 100% of the cases. So this number would just be selected over and over and over until you run out of digits and complete. So that's not a major issue. Right, do the same, but always choose the least one. So this should be quite a bit faster because it has to do fewer iterations, or the set will be a lot smaller faster. Finally, to find the life support, multiply them together. Use the binary numbers in your diagnostic report to calculate the oxygen generator rating and CO2 scrubber rating. Then multiply them together. Okay. Right. That's interesting. So now we need to store these, and we need to be able to filter them in and out. Right. Thinking like we can do this a couple of different ways. We can speed here won't really matter. We only have 1,000 items. So we could easily turn this into a sequence and then just delete entries from our sequence. And then just read the whole thing in again and do the epsilon rate thing. And we have to do 2 passes on each of them because we need to calculate the average. So actually we could save ourselves from a pass by calculating the average on the previous pass. Otherwise, we could also store this in a tuple. So one tuple with a value and one tuple with a number, or with a is chosen flag or something similar. That would mean we would have to loop through them more, but we wouldn't have to delete them out of our sequence and then read them back in for the epsilon rate. I don't think like NIM has this in secutils. We do have like when you delete something, you have delete, but you also have del. At least you used to. Is that not a thing anymore? Oh, I guess this is just in here. Yeah. It's not in the secutils module. So we have del and we have delete. Del is an O1 operation, but it messes with the order. So basically sequences are just a long bunch of memory that stores how much memory we have and how much memory we actually use, because we can allocate more memory than we actually use. What del does is that it moves the last thing into, like, it copies that into the position in the sec that we want to delete, and then it just decreases the size by 1. So this obviously messes with the order. Like you see here, if we delete the second one, so if we delete this, then 14 is gonna replace 12 in the sequence, and then the last element is gonna be removed. Delete, on the other hand, keeps the order, but has to allocate basically a whole new sequence and then move everything, like copy everything over by 1. So that it's an ON because it depends on how much stuff is after the element you want to delete in the list. But for us, the order doesn't matter at all, so we can use del. So I think we could actually just start all over. Import secutils. I guess we want to do something else, and then the CO2 numbers as we have in secutils. I think it's called collect or something, or 2sec maybe, which takes 2sec, which takes an iterator, anything that can be iterated over, and turns it into a sequence. So we can do input.txt.lines.2sec. Yep. And then we can do what was it? CO2 and O2? CO2 scrubber and oxygen generator. I'll just call them oxy numbers is equal to CO2 numbers. So that just copies that sequence. And now we do, we must loop. Okay, so let's do this. Let's actually do this. Oxy numbers, because that's the way the rules are defined in here. It first explains oxygen and then it explains CO2. That makes a bit more sense. So for so we need to calculate the average. Oxy average is equal to 0, and then for number and oxy numbers, so the first position oxy average, so if this is equal to a 1, we add a 1, otherwise we add a 0. So this is basically a ternary operator in NIM. I didn't explain that in the last one, but this is basically a ternary operator. NIM doesn't really have a separate concept for ternary operators. Everything that is a block just returns the last value from that block, which is kind of similar to a lot of functional languages. So I have an article about this, tips and tricks with implicit return. So as you can see, even like a procedure, you can do just type a string into your procedure, and since it has the string return type, it will just return this. And we can do this with ifs. We can do, of course, we can turn them into a block and use if and else and all of that stuff. We can also do other stuff, and we can do other stuff and then return something. We can also do the same with case statements, try statements, which is a nice way of doing default values. So this will return a float or throw an exception. When that exception is thrown, we return this instead. You can also just create blocks of code, just arbitrary blocks of code. And you can even do this with loops. So you can say, like, we can do this, for example, and calculate the sum inside there. But we need to initialize it first. Of course, we need to add that, and then the AoC average is AoC average divided by AoC numbers dot length. So the length of the numbers that we have. So that should calculate the average for the first character, which is basically the same that we do here. But we don't do it all at once, we do it in the beginning. Actually, I got an idea. This can be interesting. Let's do this. We don't need the line count anymore. Just let's keep the count. And let's do that. And for IC inline, do that. So now we've done all of the averages. Well, that wouldn't really be any faster. I was just thinking like we could just subtract as we removed them, but that wouldn't be a good idea. So now we need to delete numbers in our AoC numbers sequence based on if it's the average or not. And of course we need to do AoC average should of course still be equal to this thing. AoC average AoC numbers dot length. So yeah, now AoC average, the average number is either a 1 or 0. So for we need to do this by, we want to loop and we want to delete, but we can't delete stuff from a sequence as we're looping over it, because that would throw an error. You can't change the size of a sequence as you're iterating over it in NIM. So we could go for I in kind of situation, but we could also do AoC numbers dot filter it, so filter by iteration, and now we have a variable in here called it, and then we can say if it's 0 is equal to right, that is a string, but this is a number, so we do the ordinal value of that minus the ordinal value of 0. That's an easy way of turning a number between 0 and 9 into a number between 0 and 9. Is equal to the AoC average. Actually, we just need that, because that returns a bool, and we want to keep it if it's equal to the average. And here, of course, we want this. And then do AoC numbers equals this, because filter it returns. Right. That should work. Let's try this. This is starting to become a bit more complicated. So just to make sure that we're correct, let's create another file, input example. We want to, these are the example numbers that I just copied out of the task. And we can do input example. And now we can echo out all the numbers that we capped. Oops, part 2. Nope. Right, so these are the numbers that we capped. And they are all starting with 1, which should be correct. Keep only numbers selected by the bit criteria to find oxygen generator rating, the most common value. So in the example, start with all 12 numbers, consider only the first bit of each number. There are more 1 bits than 0 bits for the first iteration, so keep only the 7 numbers with a 1 in the first position. And those are these 7, which appears to be the same 7 that we have. Great. So now we just need to run this. We need to calculate an average, and we need to run this for each round. What I want to do is new AoC average is equal to 0. And I want to turn this back into a block. As I said, this will be returned automatically. New AoC average. Just do this. And in here it's called it because it's an iterator. And do that for the 1, so the next bit in our sequence. And then do this. AoC average is equal to the new AoC. If the new AoC average is larger than this, and I want to echo out this the newly calculated AoC average. Ooh. Didn't like that. I wonder if this will work. No. Oh, of course. There we go. So yeah, I had forgot to rename this to new AoC average. So it was overriding the average that we're using down here. So it didn't keep anything. So now as we're looping through and filtering out these, we're already looking at the next one. So as we're selecting these, we're already calculating the next one. We do, however, have a bug here because we consider all of them and not only those that we keep. So we want to create a variable saying if we're going to keep them, and if we're going to keep them, we do this. And then we return keeping. So now we consider only these in our average making because we only consider the ones that we're keeping. Right, so the AoC average, yeah, so the average of these should now be 1, and that's 1, 2, 3, and 1, 1, 2, 3, 4 with a 0. So that's not correct. Let's show what this count shows. Yeah, so it counted 3. It counted the correct number of ones, but it somehow messed this up, and that is because of this. So we need to do normal division, and then I guess we can floor this and turn the result of this back into an integer. Ooh. Oh, floor is defined in the math module. There we go. That still returns 1. What is this number? So that returns 3. So if I do that, it should be correct. Yes. And that should hopefully be general. Right. So well, we can keep that. So now we need to loop this. And we can do this while oxynumbers.length is not equal to 1. We do this. And we do this. And this should be I, and this should be I plus 1. And we increase our I. So basically, look at the current one and the next one, and do this. We can also add in a check here in case we get to the end, if keeping and I is smaller than 12. Bit of hard coding there. I guess we could say it.length instead. Actually, yeah, it.length. So now, okay, it errors out here. Interesting. What does that error out? And I needs to be smaller than iterator.length. Oh, right, of course. Because we're adding 1 to it. Actually, this needs to be smaller than iterator.length. There we go. So the you might have seen me write is smaller than high. So high is the highest index. So length is the length. High is the highest index I can use. This is technically correct because high in this case is 1 less than length. Whichever you want. I can also say if I is not equals to high, so if it's not the last one, we can safely do it. It's just a matter of style, what you prefer there. So now we end up with this one as the last one, which is actually not the correct one, because this says that, yeah, so this is where we run into issues. So this divided by 2 is 1, and one sample is not strictly greater than 1. So I guess we should do this. Yeah, there we go. So I changed this to greater or equal because we want to, in the case where it's an equal amount of both of them, we want to choose the one with the 1 in it according to our rules. But then I couldn't floor it because that would cause an issue when we only have 7 numbers, because that would choose the wrong number. So yeah, that boiled that down nicely. So we don't really need to echo out any of these. And then we can say echo out parse. Oh, that's in string utils. We have a parse bin function. Parse bin int. Parse is a binary integer. And it can have one of the following prefixes, but it doesn't have to. So now we can do octa numbers 0. This we filter until the length is equal to 1, so we know that we have 1 value when we get there. And now we can see that this should be 23, which is this. So for the CO2 scrubber, we basically need to do the same thing, but we need to keep the least selected one. So now we basically need to just do the exact same thing. But now, let's see, just do a replace on AoC for CO2. So now this should now, of course, give us exactly the same number, which is not what we want. Oh, and do that. That gives us the exact same number. What we want to do now is we want to do this average and select the least average one. So our keeping rule here is that it's not equal to the average. Okay, that selects the number 10, which seems to be correct. And now we just need to time these two together. There we go. So time that by this. And that is our result, 230. Now, since I didn't hard code in that 12 there, or that 5, I guess it would have been, we can now do this because everything is dependent on our input. And we get a number out, and that should be the correct number. Hurrah! Right, that was easy enough. We could, of course, have made this into a procedure or a template. Like now we're doing the same thing twice. So basically the only thing that we change is what we take in, the numbers that we're operating on, and this single check here. So we could do something like template reduce, for example, numbers is an untyped, and operation is untyped, and that returns untyped. And then we could do something like this. Just let's let's see, just rename this just to average. Rename this to just numbers. I'm not sure if that works. Oops, I did it up here as well. And yeah, presumably down here. There. Of course, this new AoC average just be our new average. And this right here should be, oh, I guess we can't pass an operation like that. Let's just do operation like this, and let's say let it dirty equal to it, and we need the average. Oh, I guess it's inject, not dirty. Dirty is something that you apply to the whole template. There we go. And now we can say AoC numbers dot reduce, and the operation we want to do is ord it. I guess we also need to, well, we can do num is not equal to average. This should of course be equal, and let's not do that, but let's num be let num be this thing. Oh, and we want to inject that. And then we can do CO2 numbers not equals, and do that. Ooh. Oh. That was the rename issue. Redefinition. Ah, right. Because I inject that. Can I not inject that? Will it be able to see this? No. And if I mark this, oops. If I mark this whole template as dirty, yeah, that just injects everything, which isn't any better. Let's just do this. Create a new scope for it. And this, of course, is just new average. I'm not sure why I didn't rename that. So this should give us the same, yeah, same number. So basically what this is a template, it takes in code. It's not a procedure. This is just going to be expanded on compile time. Inject here just means make this variable visible to whatever these things are. So I can use num and average in sort of this operation because I've injected them. It's a bit of a hacky way of doing it. We could have done a procedure as well that took numbers, var numbers, and an operation as a closure or something, and effectively have done the same thing. But then we would have needed a bit more sugar down here. But yeah, that's part 2. A bit trickier than day 3. a bit trickier than the previous days, but not terribly so. You have right. You have a question here. Possible to catch up on AoC. Table 1 looks very easy. I'm doing that. Oh yeah, it's totally possible to catch up. I mean, you can go and you can have a look at these. I mean, you can even have a look at earlier years as well. So it's totally possible to catch up. The first ones are typically fairly easy. But yeah, that was everything from me. This one has been running on for a bit longer than I expected. So that was it for me today. Sorry that it was a bit, maybe felt a bit rushed. But yeah. So hopefully see you guys tomorrow.